The study of deformation in and fracture materials is called mechanical behavior of materials. And the knowledge of this area will provide the basis for avoiding these types of failure in engineering application. Machines, vehicles, and structures must achieve a acceptable level of performance and economy while safe and durable at the same time. So it is necessary for us to avoid excess deformation, such as bending, twisting, and stretching of the materials. Cracking in components must be avoided completely or strictly limited, so it will not progress to a complete fracture. Basically, in a mechanical behavior of materials, topics that will be covered include elastic and plastic deformation, creep, fracture and fatigue of materials, including crystalline and amorphous metals, semiconductors, ceramics, and polymer. And it will focus on the design and processing of materials from the atomic to macro scale to achieve desired mechanical behavior. So why do mechanical properties important? Material testing is often the last step in the manufacturing process, and yet the quality is the result of both the process and the material. If the material that goes into the product is defective, then the product may be defective. So in the process of forming materials, understanding the material's properties can help to better predict the manufacturing outcome. And for manufacturers, it is very important to understand the mechanical properties of materials that exhibit some Hookean behavior during loading. It is important because the performance of a structure is frequently determined by the amount of deformation permitted, and some measured properties that must be considered when we want to design something or when we designing a structure include a tensile strength, yield strength, and Young's modulus of elasticity. A Thomas iterative tetrahedron is a schematic framework that explains the complex relationship in the field of mechanical behavior of materials. The successful utilization or application of a material requires that they satisfy a set of property, and these properties can be classified into thermal, optical, mechanical, physical, and nuclear, and they are closely connected to the structure of materials. And the final structure is the result of synthesized and processing. So a schematic framework that explains the complex relationship in the field of the mechanical behavior of materials is what we call as a Thomas iterative tetrahedron, which contains four principal elements, like what we can see in the figure here. We have mechanical properties. We have a characterization. We have a theory, and we have a processing. And these elements are related, and change in one will affect the changes in others. And so we have an example of Thomas iterative tetrahedron in automotive industry. The application of the tetrahedron of material science and engineering to produce sheet steels for automotive chassis. And we can see here, we know that the composition, the microstructure, and the synthesize and processing are all interconnected, and in the end will affect the performance to the cost ratio. The property of material is crucial to the application it can be applied to, and it is very important and necessary for the design, specification, deformation, and failure estimation, microstructure property relation, selection of the material, and also in terms of economic consideration. Matter is anything that has mass and occupies a space. And a useful way to start thinking about a matter is to think about the different materials or substance that it can be made into. And these materials make up the object about us, and each of these materials has a different properties or characteristic that can be observed or tested. Scientists, technologists, and engineers investigate these materials. They experiment with them and compare them, compare their properties, and relate the result to possible uses. So now we will talk about testing of materials to determine its mechanical properties. Here is how we can classify material testing. First, we can classify materials testing based on destructive and non-destructive testing. So in destructive testing, the specimen is damaged beyond use. For example, we have a bending testing, tensile testing, and impact testing. That are some examples of destructive testing. Non-destructive testing, on the other hand, is where the material is not damaged or harmed. For example, if you want to determine the structural integrity of pipeline, NDT is the most suitable way for that purpose. And here we have some examples of NDT testing. We have ultrasonic testing, we have eddy current, we have radiographic testing, we have magnetic particle testing. And also we can classify testing of materials based on scientific testing and commercial testing. In scientific testing, more careful and precise measurement of a property with aim to supply accurate data for research and design. And on the other hand, we have a commercial testing with the purpose to check if the materials meet this specification to establish a degree of quality control. We don't want engineering materials to fail because they can cause loss of life, economic loss, or a loss of a product or services. The usual causes of material failure are incorrect material selection, incorrect processing, incorrect manufacturing procedure, or inadequate design. Failure is defined as any change in size, shape, or material properties of a structure, a machine, or machine parts. Or in other words, a part becomes unable to satisfactorily perform its intended function. It is important to understand the mechanics of various failure modes. Failure is always undesirable because it will put human lives in danger, it will cause economic losses, and will interfere with the availability of a product and services. And commonly, the causes of failure are improper material selection, inadequate design, and also processing. So first, maybe it is important for us to define what is a fracture. We can define a fracture as a separation of a body into two or more pieces in response to applied stress at a temperature that is relatively low to the melting temperature of the material. So how does fracture occur? Fracture occurs when the metal or material experiences a stress that exceeds its yield strength. Fractures can occur in three different types. That is a ductile fracture, moderately ductile fracture, and a brittle fracture. So deformation can be divided into two. That is a time independent, such as elastic and plastic, and also a time dependent, such as a creep. Fracture, on the other hand, can be due to the static loading, that is either brittle or ductile, due to environmental and creep rupture. And in addition to that, fracture can also be due to the fatigue or cyclic loading, that is either high or low cycle, and crack growth can occur during fatigue. So now I want to talk about a ductile and a brittle fracture. So we have a ductile fracture that can be defined as a fracture that occurs without plastic deformation, and this is the most preferred in most situation. And then we have a brittle fracture that happen with a little or no plastic deformation, and thus they are catastrophic, meaning that they can occur without warning. And this is how we can show a fracture behavior of a very ductile, moderately ductile and a brittle material. And so we can see here for a very ductile material, the specimen neck down to a point here in the middle. And here we have a failure for a moderately ductile material. And then we have a brittle material here, where we can see that deformation is very small and fracture occurs without warning. And here we have an example of a failure of a pipe. We have a ductile failure, and like what we can see in the figure here, we can see that the pipe is still in one piece, and we can see a very large deformation happen. And then we have a brittle failure where the pipe broken into many pieces, and we have a small deformation that happened. And we can see that the specimen shatters to many pieces during the failure. So now let's talk about steps that are involved in moderately ductile failure. And this is actually a really common type of failure. And we can see that here we have the stages that involve in moderately ductile failure. It started from necking, and then we have a void nucleation, and then the void growth and coalescence, and then we have a shearing adhesive phase, and finally we have a fracture. So the fracture lines always occur at a 45-degree angle, and below here we have scanning electron microscope images of failure specimen. And fracturographic analysis is very important. Oftentimes scanning electron microscope is used to acquire the fracture surface. We want to figure out why the part broke in the first place, and what we can do in the future in terms of processing and maybe the material selection to avoid fracture from happening. And here we have the naked eye image of ductile versus brittle failure. And here we have a cup and cone fracture. And then we have a brittle fracture of a specimen. We can see that for a brittle fracture, it has a very flat surface compared to the cup and cone fracture of ductile and moderately ductile material.